Okay, let's dive right into this explainer. Today, we're taking a subject that literally strikes fear into the hearts of many, material and energy balances, and we're going to completely transform all that intimidating abstract algebra into a crystal clear visual system. Seriously, if you have ever stared at a dense page of chemical equations and wondered how on earth to even begin solving for unknown flow rates, you are in exactly the right place.
Because, this is a very serious question. What actually stands between a highly profitable chemical process and a catastrophic runaway reaction? Well, the answer is incredibly foundational. Millions of dollars and actual human lives depend on getting these basic algebraic balances right. So today, we're going to show you exactly how to master them without getting completely bogged down in dry math. We are going to visualize the invisible.
Look, we don't just crunch these numbers for fun, right? Every single calculation we do is tied directly to either safety or profit. On the safety side, we're calculating enthalpy changes and energy balances for a very real reason, to ensure we can remove heat fast enough to prevent a runaway exothermic reaction. And on the profit side, we're meticulously performing mass balances to track every single kilogram of product, finding leaks and inefficiencies to completely minimize raw material wastage. This math is quite literally the blueprint for a safe, lucrative plant.
So here is our roadmap for today. First, the system boundary. Second, the basis hack. Third, mapping the PFD. Fourth, the DOF sanity check. Fifth, the core equations. And sixth, the MEB workflow.
Let's kick things off with Section 1, the system boundary.
Now, this is arguably the single most important skill for any process engineer, and the best part is, it's an entirely visual concept. To solve any complex process, you absolutely must define what is inside your system and what is crossing its boundaries. Think of a system boundary as a conceptual dashed line that you draw around a piece of equipment, maybe a whole plant, or even just a pipe intersection. By accounting for the material entering and leaving this very specific boundary, we can pinpoint mass flows that would otherwise be completely unknown or literally impossible to measure.
And that leads us to the brilliantly simple black box approach. Imagine drawing that dashed boundary right in the center of your diagram. By doing this, we isolate our system. You see, we don't necessarily need to know every chaotic, complicated thing happening inside that box right away. We just need to account for what crosses that dashed line, what mass inputs are coming in from the left, what outputs are exiting to the right, and what energy, like heat, which we label Q, or work, which we label W, is crossing that boundary. This visual isolation is your absolute best friend.
Moving on to Section 2, the basis hack.
So once we have our boundary, we often look at the paper and wonder, okay, where do I even begin the math? Well, experienced engineers use a brilliant hacker tip for this, the magic number 100. If a problem throws a bunch of percentages or fractions at you, but zero actual flow rates, and you are totally stuck, just assume a basis of calculation of 100. It could be 100 kilograms per hour, 100 moles, whatever fits. Why? Because it instantly makes mass fraction math 10 times easier. Think about it. If a stream is 30% solids and 70% water, a basis of 100 kilograms means you literally have 30 kilograms of solids and 70 kilograms of water. Boom! You've instantly turned abstract ratios into concrete, workable numbers.
Next up, Section 3, mapping the PFD.
All right, we have our boundary and we have our basis. Next, we need to map our physical plant using a process flow diagram, or PFD for short. Every major piece of equipment gets a specific letter designation. You've got P for a pump, E for a heat exchanger, R for a reactor. By linking these symbols with flow lines, we build a complete visual topology of the entire plant. You just label the streams consecutively, stream 1, stream 2, and so on, and suddenly the overwhelming chaos of a massive industrial facility is reduced to a clean, logical roadmap.
Let's see this in action. Imagine applying this to a clarifier. We draw our dashed system boundary around the clarifier and we deploy our basis hack. Let's say 100 kilograms per minute of slurry inlet. Now, if that inlet is 50% solids, that's 50 kilograms of solids and 50 kilograms of water. Simple, right? Now, if our equipment operates at a 60% solid removal efficiency, the clarified water outlet is still going to contain 40% of the original solids, which is 20 kilograms per minute. That leaves 30 kilograms to exit via the extracted solid stream. By measuring just one combined output flow, let's say it's 65 kilograms per minute for the water outlet, basic subtraction tells us the remaining 45 kilograms is water, meaning 5 kilograms of water exited with the bottom solids. By just setting up a simple table with a 100-unit basis, we've completely uncovered exactly how the mass is distributed across the entire boundary.
Which brings us to Section 4, the DOF sanity check.
Now, you might be super tempted to just start throwing algebra at the wall to see what sticks. But hold on. Before we do pages of calculations, we must perform a crucial sanity check, also known as a degree of freedom, or DOF analysis. You count your unknown variables, and then you subtract the number of independent equations you can write. Here is the golden rule. If your degrees of freedom calculation does not equal exactly 0, the system is unsolvable. If it's greater than 0, you're missing information. Less than 0, your data is overspecified and might contradict itself. So if DOF is not 0, stop calculating immediately. I mean it, put the pencil down. You will save yourself hours of wasted effort. And honestly, this is exactly what separates process engineering professionals from students.
Section 5. The core equations.
So once your DOF hits 0, you get the green light. It's time to bring in the foundational laws of the universe to actually solve for those unknowns. What you're seeing is the ultimate governing equation for mass. What goes in, plus what is created by a chemical reaction must equal what goes out, plus what builds up inside, plus what gets consumed by a reaction. It is an absolute law of conservation. And let me give you a beautiful shortcut. If your plant is running normally, it's at what we call steady state. At steady state, things like temperature and concentration aren't changing over time. And because of that, that messy, complicated accumulation term neatly drops to exactly 0.
And guess what? The exact same logic applies to energy. We balance the internal energy, the kinetic energy, and the potential energy of the mass streams flowing in and out. But remember, energy can also cross our dashed system boundary without any mass attached to it, specifically as heat, which we call Q, and work, which we call W. By clearly defining our reference states, we can figure out the specific enthalpy of every stream and balance the heat requirements to guarantee our process is both thermally safe and highly efficient.
Finally, Section 6, the MEB workflow.
All right, we've covered the stakes, the visual tools, the calculation hacks, and the math itself. Now let's put it all together into a repeatable system. Get your cameras ready, folks, because this is the screenshot moment right here, the ultimate 5-step material and energy balance workflow cheat sheet. Step 1, specify that magic 100-unit basis and completely label your PFD. Step 2, visually identify your systems by drawing those dashed boundaries. Step 3, perform that degree of freedom sanity check. Demand that it equals 0. Step 4, write out your input-output equations based on those boundaries. And only then, in Step 5, do you execute the math to solve it. Follow this workflow, and I promise you, you won't get lost in the algebra. It's pretty amazing how drawing a simple dashed box can totally tame the most complex industrial calculations, turning pages of terrifying equations into a reliable, visual tool for maximizing safety and profit. But now I really want to hear about your real-world battles with these systems. What is the absolutely most difficult process simulation software or manual calculation method you've ever had to tangle with on site? Have you ever gotten stuck with a degree of freedom that just flat out wouldn't hit 0? Drop your toughest calculation challenges in the comments below, and let's figure them out together. Until next time, keep your boundaries clear and your balances steady.